All right, welcome to the deep dive. Today, we are going deep into the world of differential equations.
Sounds exciting.
It is, actually. I think it's going to be a lot of fun. We've talked about differentiation and integration before, like back in Class XI in Chapter 5.
Right.
And differential equations, they kind of take that and just, build on it.
Yeah, they definitely do. The core idea with differential equations is, instead of taking a function and finding its rate of change, which is
Yeah.
what we do with differentiation,
Mm-hmm.
we're kind of going the other way around. We're starting with information about how a function changes,
Yeah.
and we're trying to find the original function.
Right.
So
Yeah.
say we have something like diddy x equals g of x, right?
Okay.
Can we actually go back and figure out what the original function y was?
Oh, that's really cool. So it's not just about finding a number. It's like we're trying to find a whole function.
Exactly. It's a whole function that describes, how something is changing.
Okay. So now why should our listeners care about this? Why are differential equations so important?
Well, differential equations are really everywhere. They're the language of change
Wow.
in the universe, right?
Right.
Like they pop up in physics, in chemistry, biology, even in fields like anthropology and geology, economics.
Really?
Yeah, anything that changes over time or space,
Okay.
you could often describe it using differential equations.
So basically it's like fundamental to understanding a lot of what's happening around us.
Absolutely. It's a powerful tool.
All right. So what's our plan for this deep dive? What are we going to cover today?
Well, we'll start with some basic vocabulary.
Okay.
Right? The basic concepts that you need to know. And then we're going to look at what are called general and particular solutions.
Okay.
We're going to explore how to create these equations from known solutions.
Ooh, cool.
Right? And then we're going to look at some methods for solving some of the fundamental types of differential equations. Specifically, first-order, first-degree differential equations.
First order, first degree. Does that mean there are other more complicated ones?
Oh, absolutely. There are more complex differential equations.
Okay.
Like we have ordinary differential equations, which is what we're going to focus on today,
Yeah.
which only involve one independent variable.
Right.
But then there are partial differential equations,
Yeah.
which have multiple independent variables. And those are for another deep dive.
Yeah, that sounds like a lot.
Yeah, we'll stick to the ordinary ones for now.
Okay, so just one variable at a time. Now, before we get into it, I've noticed there are different ways to write derivatives.
Right.
What's the deal with like y prime, y double prime, y triple prime, and y to the n?
Yeah, those are just different notations for derivatives.
Okay.
So y prime is the same as dx.
Uh-huh.
Y double prime is the second derivative,
Makes
dx,
sense.
and y triple prime is the third derivative,
Right.
and y to the n is just the nth derivative.
Okay.
It's just a way to make the notation a bit more compact,
Right, it's a shortcut.
especially when you're dealing with higher order equations.
So you don't have to write out those big fractions all the time.
Yeah, exactly. Just keeps things clean.
Makes sense. Okay, let's get into the first two big concepts, order and degree.
All right, those are important.
What do these terms tell us about a differential equation?
Okay, so the order of a differential equation is just the highest derivative that appears in that equation.
Okay.
You can kind of think of it as like the sensitivity of the equation to change.
What do you mean by that?
So a higher order equation means it's reacting to more levels of rate of change,
Oh, interesting.
right? So if you have an equation like dx equals e to the x,
Okay.
the highest derivative there is the first derivative.
Right.
So it's a first order differential equation.
There's order. Okay.
But if you have something like dxx plus y equals 0,
Okay.
now the highest derivative is the second derivative, so it's a second order equation.
Got it. So it's like how many layers of change is the equation dealing with?
Exactly. That's a good way to think about it.
All right. Give me another one just to make sure I'm getting this.
Okay, how about this? Dot x plus the quantity dx squared plus x equals 0.
Okay, so the highest derivative there is the third derivative. So it's a third order equation.
Exactly, you got it.
All right, so highest derivative equals order. Now, what about the degree?
Okay, so the degree of a differential equation is the highest power to which the highest order derivative is raised.
Okay.
But there's a catch. The equation has to be a polynomial equation in the derivatives.
What does that mean?
It means that things like y prime, y double prime, those can only have non-negative integer exponents.
Okay.
You can't have like sine of y prime or logarithm of y double prime, things like that.
So it's got to be like a prime squared, y triple prime cubed, that kind of thing.
Exactly. No fancy functions acting on the derivatives themselves.
Right, just plain old exponents. All right, so give me an example where the degree is easy to see.
Okay, how about this? Open parentheses, dx squared, close parentheses squared, plus dx squared minus dx plus y equals 0.
All right. The highest derivative is the third derivative, and it's squared.
Right.
So the degree is 2.
Perfect. That's exactly right.
Okay. What if it's not a polynomial equation in the derivatives? What happens to the degree then?
If it's not a polynomial equation in the derivatives, then the degree is simply not defined.
Okay.
So, for example, if you have something like open parentheses, the dx, close parentheses squared plus sine of dx minus y equals 0.
Okay.
Because of that sine of dx term, it's not a polynomial in the derivative.
Right.
So the degree is not defined.
So the degree only exists if it's a nice, clean polynomial.
Got it. Are order and degree ever like 0 or negative?
Nope. Order and degree, if they're defined, are always positive integers.
Positive integers.
They tell us something fundamental about the structure of the equation.
Cool. Okay. Time to test my understanding a bit. Let's look at some examples.
Yep. What's the order and degree of cosine of dx minus x equals 0?
All right, walk me through it.
Okay, so the highest derivative is dx, so the order is 1.
Good.
But then we have cosine of dx.
Right.
So that's not a polynomial in the derivative.
Exactly.
So the degree is not defined.
You got it.
Okay, next one. Did cosine dx quantity cubed plus dx minus x times y equals 0.
Right.
The order is 2 because of the dx.
Yeah.
And it is a polynomial in the derivatives.
Mm-hmm.
And the highest power of that second derivative is 3.
Yes.
So the degree is 3.
You're in a hole.
Okay, last one. Y to the fourth prime plus y double prime plus e to the y's equals 0.
All right, challenging one.
Order is 4 because of the y to the fourth prime. Now for the degree, we've got e to the y, which is a function of y,
Right.
but not the derivatives.
Mm-hmm.
So it is a polynomial in the derivatives.
Yes.
And the highest power of y to the fourth prime is 1.
Correct.
So the degree is 1.
Nailed it. You've got a good grasp of order and degree.
Okay, so the order tells us the most powerful rate of change involved, and the degree tells us how complicated that highest rate of change is.
Exactly. They give us a sense of the complexity of the equation.
Okay. Now, what's next on the agenda?
Next up, we're going to talk about general and particular solutions.
Sounds like we're moving from describing the equation to actually finding the solutions.
Absolutely.
Yeah.
In algebra, solving an equation means finding numbers that make the equation true, right?
Right.
But in differential equations, we're not solving for numbers.
Okay.
We're solving for functions.
So instead of a point on a number line, we're finding a whole curve that fits the equation.
Exactly. And these functions, when you substitute them back into the differential equation, they make the equation hold true. And the graph of such a solution, we call it a solution curve or an integral curve.
Interesting. So what's the difference between a general solution and a particular solution?
Okay, so a general solution is a family of functions that satisfy the differential equation. It will usually have some arbitrary constants in it, parameters that can take on any value.
Right.
A particular solution is what you get when you assign specific values to those arbitrary constants.
Oh, okay. I see.
So you can think of the general solution as giving you all the possibilities.
Right.
And a particular solution is like a specific instance of that general solution.
So the general solution is broad and the particular solution is specific. Can you give me an example?
Sure. Let's take the differential equation d bu dx plus y equals 0.
Okay.
The general solution for this equation is y equals a cosine of x plus b sine of x,
Okay.
where a and b are arbitrary constants.
Right. So those constants could be anything.
They could be anything else.
And that would still solve the equation.
Exactly.
Now, how would we get a particular solution from that?
Well, if we were given some initial conditions, right?
Wait.
Like, let's say y of 0 equals 1
Okay.
and y prime of 0 equals 0.
Right.
We could use those conditions to solve for a and b and find a particular solution.
Oh, so it's like extra clues that help us narrow it down.
Exactly. Like in this case, the particular solution would end up being just y equals cosine of x.
Oh, okay. So A equals 1 and B equals 0 in that case.
Exactly.
Got it. All right. Let's actually try verifying a solution, see if it works.
Sounds good.
Okay, so verify that y equals e to the negative 3x is a solution of dx x plus to dx minus 6, y equals 0.
All right, good one. So first you need to find the derivatives of y.
Right. Okay, so dxx is negative 3e to the negative 3x,
Yes.
and dxx is 9e to the negative 3x.
Perfect.
And now we just substitute those into the differential equation.
Exactly.
So we've got 9e to the negative 3x plus negative 3e to the negative 3x minus 6 times e to the negative 3x. And that simplifies to, let's see, 9 minus 3 minus 6, which is 0.
And 0 times anything is still 0.
So it works. It's a solution.
You got it. It satisfies the equation.
Okay, let's try another one. Verify that y equals a cosine of x plus b sine of x is a solution of d sine plus y equals 0.
All right. Same idea.
So we already found the derivatives earlier.
You did.
d x is negative a sine of x plus b cosine of x.
Right.
And d del x there is negative a cosine of x minus b sine of x.
Yes.
Now, plugging those into the equation, we get negative a cosine of x minus b sine of x plus a cosine of x plus b sine of x. And look at that. Everything cancels out. We get 0 again.
Perfect. It's a solution.
Okay, so verifying solutions is just plugging and chugging.
Pretty much, yeah. It's a good way to check your work.
Now, how many arbitrary constants should we expect to see in a general solution? Is there a way to tell beforehand?
Yeah, there's a helpful rule.
Okay.
The number of arbitrary constants in a general solution is equal to the order of the differential equation.
Oh, that's a nice, easy rule to remember.
So a first-order equation will typically have one arbitrary constant.
Okay.
A second-order equation will have 2,
Yeah.
and so on.
That makes sense. All right, now let's switch gears a bit. What about forming differential equations? It sounds like we're going in reverse.
We are. We're going to start with a general solution, which, remember, has those arbitrary constants.
Right.
And the goal is to eliminate those constants through differentiation
Oh, interesting.
and arrive at a differential equation that solution satisfies.
So we're going from the answer back to the question.
Okay.
How does that actually work in practice?
All right, so let's say you have a family of curves
Okay.
defined by an equation with some arbitrary constants, right?
Right.
What you do is you differentiate that equation with respect to the independent variable.
Okay.
And usually each time you differentiate, you can eliminate one of those arbitrary constants.
Oh, okay.
And the order of the resulting differential equation will match the number of constants you started with.
So if we have one constant, we differentiate once. Two constants, differentiate twice.
Precisely.
Okay, let's see a simple example of this. Let's take a family of circles centered at the origin.
Oh.
So the equation is x squared plus y squared equals r squared.
Right, r being the radius, the arbitrary constant.
Right, exactly. Now we differentiate both sides with respect to x.
Oh, that's good.
So that gives us 2x plus 2y times dx equals 0.
Right.
And we can simplify that to x plus y times ddx equals 0.
That's it.
And look at that, the r is gone.
Gone.
And we have a first-order differential equation because we started with one constant.
That's exactly right. So you see how we formed a differential equation from a family of curves.
Right, we went from the circles to the equation that describes them.
Exactly.
Okay, now let's try some more examples. What if we start with y equals mx, where m is an arbitrary constant?
All right, go ahead and differentiate with respect to x.
So dx equals m.
Yes.
Now, to eliminate the m, we can substitute this back into the original equation.
Oop.
So we get y equals d dx times x.
Right.
And rearranging that, we get x times d dx minus y equals 0. And again, it's a first-order equation because we had one constant to eliminate.
You got it.
Okay, next one. Y equals a sign of open parentheses x plus b close parentheses, where a and b are arbitrary constants.
All right, two constants this time. What do we do?
Differentiate twice.
You got it.
Okay, so the first derivative is d dx equals a cosine of open parentheses x plus b close parentheses.
Good.
And then the second derivative is dx xu equals negative a sign of open parentheses x plus b close parentheses.
Perfect.
Now, if we look closely, that negative a sign of open parentheses x plus b close parentheses, that's just our original y.
It is.
So we can substitute that in, and we get dx simul equals negative y,
Right.
which we can rewrite as dxx plus y equals 0.
Exactly.
And that's a second-order equation, which makes sense because we had two constants.
Perfect. You're getting the hang of this.
Okay, let's try something a bit more involved. How about the family of ellipses with foci on the x-axis and center at the origin?
All right, good one. What's the equation for that?
The equation is x squared over a squared plus y squared over b squared equals 1.
Okay, A and B being the semi-major and semi-minor axes are arbitrary constants.
Right. Now, we need to differentiate this twice.
Exactly.
Okay, so the first derivative, 2x over a squared plus 2y over b squared times d dx equals 0.
Okay, keep going.
And we can simplify that a bit. X over a squared plus y over b squared times d at x equals 0. Now for the second derivative.
Remember the product rule.
Right, okay. So we get 1 over squared plus 1 over b squared times d x times dx plus y times d x equals 0.
Good.
Or 1 over squared plus 1 over b squared times the quantity d x squared plus y times d x equals 0.
Excellent.
Now, we have these two equations with a squared and b squared, and we also have the original equation.
Right.
And we need to use all of them to get rid of a squared and b squared. This looks like it might take some work.
It might take a little bit of algebraic manipulation.
Yeah, let's see. Okay, I think I've got it. After a lot of simplifying, we get x times d x squared plus x times y times d dxi minus y times d dx equals 0.
That's it. You got the correct differential equation.
Wow, that was a bit of a workout.
It can get tricky sometimes, yeah.
But it's really neat how the order of the equation matches the number of constants we had to eliminate.
Exactly. It's all connected.
Okay, let's do a couple more examples just to get comfortable with this.
That was good.
What if we have the family of circles touching the x-axis at the origin?
All right. What's the equation for that family?
It's x squared plus y squared equals 2ay, where a is the constant.
Okay, good. Now differentiate and eliminate.
Okay, so the derivative is 2x plus 2y times did x equals 2 times did x. Now, to get rid of a, we can rearrange that derivative.
Good.
To get a equals x plus y times did x, all divided by did x.
Right.
And now we substitute that back into the original equation.
Okay.
So we get x squared plus y squared equals 2y times the quantity x plus y times do x, all divided by did x.
All right, and simplifying that.
After some simplification, we get y squared minus x squared minus 2xy times d dx equals 0.
You got it.
Or we can rewrite that as d dx equals y squared minus x squared, all divided by 2xy.
Perfect. One constant first order equation.
All right, last one for this section. What about parabolas with vertex at the origin and axis along the positive x-axis?
Okay, what's the equation for those?
It's y squared equals 4ax, where a is the constant.
All right. Take it away.
Okay, differentiating with respect to x, we get 2y times d x equals 4a.
Good.
Now, we can substitute that 4a back into the original equation.
Right.
So we get y squared equals 2y times d dx times x, which simplifies to y times d dx minus 2y equals 0, assuming y is not 0.
That's correct. Another first order equation.
Okay, I think I'm starting to get the hang of this.
You're doing great.
So we differentiate as many times as we have constants, and then we use those equations to eliminate the constant.
Exactly. That's the key idea.
All right, we've covered order, degree, general and particular solutions, and how to form differential equations.
Phew, it's a lot.
It is. But now comes the exciting part. How do we actually solve these things?
Yeah, that's the real challenge.
So we're starting with first order, first degree equations, right?
Correct. Equations in the form day x equals f of x.
Okay. What's our first tool for tackling these?
Our first technique is called separation of variables.
Separation of variables.
It's a pretty straightforward idea.
Okay, tell me more.
The goal is to rearrange the equation so that all the y terms, including dx, are on one side of the equation,
Oh, okay.
and all the x terms, including dx, are on the other side.
Oh, I see.
So you essentially separate the variables.
So we want to get it into the form g of y times d equals h of x times dx.
Exactly. And once you have it in that form,
Yeah.
you can integrate both sides
Okay.
with respect to their respective variables.
So separate and integrate.
Pretty much, yeah.
Okay, let's try it out with an example. What if we have the equation 1 plus x times d minus y times the quantity minus 2 times dx equals 0?
That's a good one. Let's separate those variables.
Okay, so we want all the y's with dx and all the x's with dx. So I think we need to divide both sides by y times y minus 2 and also by 1 plus x.
That's exactly right.
Okay, so that gives us d over y times y minus 2 equals dx over 1 plus x.
Perfect. Now, you can integrate both sides.
All right, but to integrate that left side, I think we might need to use partial fractions, right?
Yes, that's a good idea. It'll make the integration easier.
Okay, so we can rewrite 1 over y times y minus 2 as a over y plus b over y minus 2.
Okay.
And then we solve for a and b. And we get a is equals negative 1/2 and b equals 1/2.
Correct.
So the integral becomes the integral of negative 1 over 2 y plus 1 over 2 times the quantity y minus 2
Yes.
equals the integral of dx over 1 plus x. Okay, now we integrate. And we get negative 1/2 times the natural log of the absolute value of y,
Mm-hmm.
plus 1/2 times the natural log of the absolute value of y minus 2,
Ah,
equals the natural log of the absolute value of 1 plus x plus c.
don't forget the constant of integration.
Right, of course, plus c. And we can combine those logarithms on the left side
That's a good idea.
to get 1/2 times the natural log of the absolute value of y over y minus 2
Right.
equals the natural log of the absolute value of 1 plus x plus c.
Okay.
Or we can write that as the natural log of the square root of y over y minus 2 equals the natural log of the absolute value of 1 plus x plus c.
Okay. And now?
Now, we can exponentiate both sides to get rid of those logarithms.
Good.
So we have the square root of y over y minus 2 equals e to the power of open parentheses natural log of the absolute value of 1 plus x plus c, close parentheses.
Mm.
And we can simplify that to the square root of y over y minus 2 equals plus or minus e to the c times the quantity 1 plus x.
Right, because e to the power of a sum is the product of e to each power.
Yeah, exactly. Now, let's just call that plus or minus e to the c a new constant, k.
Okay.
So we have the square root of y over y minus 2 equals k times the quantity 1 plus x.
Good.
And squaring both sides gives us y over y minus 2 equals k squared times the quantity 1 plus x squared.
Excellent. And remember, k squared is just another arbitrary constant.
Yeah, we could call it something else if we want, but it doesn't really matter.
That's right. You've found the general solution.
And notice how that integration step introduced the arbitrary constant c, which turned into k.
Exactly. That's characteristic of general solutions.
Now, I think I'm starting to get comfortable with this. Let's try another one. What if we have the equation 1 plus y squared times dx equals 1 plus x squared times die?
All right, another good example. What's the first step?
Separate those variables. So we divide both sides by 1 plus y squared and 1 plus x squared.
Good.
And we get dx over 1 plus x squared equals die over 1 plus y squared.
Perfect. Now you can integrate.
Okay, so the integral of 1 over 1 plus t squared is the inverse tangent of t, right?
That's right.
So we get the inverse tangent of x equals the inverse tangent of y plus c.
And that's your general solution.
Wow, that was pretty straightforward.
Yeah, sometimes it works out nicely.
All right, let's try finding a particular solution now. What if we have diet x equals negative 4 xy squared, and we know that y equals 1 when x equals 0.
Okay, so first you need to set it up for separation of variables.
Right. So we can rewrite this as bidis over y squared equals negative 4 x dx.
Good.
Now we integrate both sides.
Mhm.
So the integral of y to the negative 2 equals the integral of negative 4 x dx.
Right.
And that gives us negative y to the negative 1 equals negative 2x squared plus c.
Yes.
Or we can write that as negative 1 over y equals negative 2x squared plus c.
Okay.
Now we use that initial condition y equals 1 when x equals 0 to find c.
Exactly.
So plugging those in, we get negative 1 over 1 equals negative 2 times 0 squared plus c.
Right.
Which means c equals negative 1.
Good job.
Now we substitute that c back into our general solution,
Okay.
and we get negative 1 over y equals negative 2x squared minus 1.
Mm-hmm.
And we can rearrange that to get y equals 1 over the quantity 2x squared plus 1.
And that's your particular solution.
All right, we found the specific curve that fits the equation and the given condition.
Exactly. You've narrowed it down from the family of solutions to the one that matches the extra information.
Cool. Okay, let's try another one. Find the equation of the curve passing through the point 1, comma 1, whose differential equation is x my d equals the quantity 2x squared plus 1 dx, where x is not equal to 0.
All right, so you're given the differential equation and a point that the curve must pass through.
Right. First, I think we should rewrite the equation to get d dx by itself.
That's a good idea.
So dividing both sides by x dx, we get d dx equals the quantity 2x squared plus 1, all divided by x.
Okay.
Which we can simplify to d dx equals 2x plus 1 over x.
Now you can integrate.
All right, so integrating both sides with respect to x, we get y equals x squared plus the natural log of the absolute value of x plus c.
Good.
Now we use the point 1, comma 1 to find c.
Right.
So plugging those values in, we get 1 equals 1 squared plus the natural log of 1 plus c.
Mm-hmm.
And since the natural log of 1 is 0,
Yes.
we get c equals 0.
Perfect.
So the equation of the curve is y equals x squared plus the natural log of the absolute value of x.
That's it. You found the specific curve that satisfies both the differential equation and the given point.
Okay, one more example for separation of variables, and then we can move on.
That's good.
Okay, this one is a bit different. Find the equation of a curve passing through the point negative 2, comma 3. given that the slope of the tangent to the curve at any point x comma y is 2x over y squared.
Okay, so remember, the slope of the tangent at any point is given by dit x.
Right, so d to x equals 2x over y squared.
Exactly.
Now we can separate the variables.
Mhm.
Multiplying both sides by y squared, we get y squared d equals 2x dx. Now we integrate both sides.
Right.
So the integral of y squared die equals the integral of 2x dx.
All right.
And that gives us y cubed over 3 equals x squared plus c.
Okay.
Now we use the given point, -2, comma 3, to find c. So
Right.
plugging those values in, we get 3 cubed over 3 equals -2 squared plus c,
Hmm.
which simplifies to 9 equals 4 plus c.
So c equals 5.
Yeah, c equals 5. So the equation of the curve is y cubed over 3 equals x squared plus 5.
That's it. You could also write it as y cubed equals 3x squared plus 15.
Okay, cool. So that's separation of variable.
That's the first technique.
It's all about getting the variables on opposite sides and then integrating.
Exactly. It's a powerful method for a wide range of differential equations.